Well, today we're going to talk about three-dimensional force systems, point equilibrium. This is section 3.4. We're going to use many of the same concepts, or all of the same concepts we used in 2 dimensions. The same methods apply. And what we're going to look for is defining the point that we care about, and then summing the forces in the x, the y, and now the z to equal to 0. Often we're going to get a 3 equations, 3 unknowns situation. So the way to get started is to define the point of interest, understand which axes are appropriate, define positives in those axes, draw the free body diagram, and label all the forces. What we'll find is that Cartesian is the easiest way of defining the forces. So Cartesian is easiest to work with. We'll break up all the forces into a Cartesian force vector. And we're going to assume a sense of direction of unknown forces. In many cases, we'll be able to know the direction. If it's a string or cable, it will be in tension. Ropes cannot ever push, can never be in compression. So most of the time we'll know that. However, if there is a rigid member, it could be in compression. And if we know that it is compression, we'll assume it's compression, we'll draw that sense of direction like that. And I've got one problem to show you that. Then to solve, we sum the forces in the x direction. We know that all the i's have to be equal to 0, and the same with the j's and the k's, and solve for the unknowns. Well, the first problem I want to visit with you about here is 378, and I just want to walk through fairly carefully with you the process on how to do this, and then you'll be able to get faster and take some shortcuts as we go along. But first of all, understand what is our point of interest. The point of interest here is point C. This is where the box is suspended from. It has 3 cables that are going to be in tension that are pulling away from that point. So first let's find our origin here, and it's going to be right there. The axes are drawn x, y, z, but I'm going to redraw those axes using our three-dimensional grid, three-dimensional axes using our graph paper, and so this will be our x, our y, and z axis on this. So let me redraw that. Let's first find point C on our new grid. So here is x, and this will be y and z. So point C is going to be 6 in the j direction along the j axis. So there'll be 1, 2, 3, 4, 5, 6. This will be point C. Let's define the other points along the way. Let's find point A. Point A is 2 in the positive I direction, and it is on this plane. So it is right along the x-axis. So that'll be 1, 2 right there. And point B is -2 on the x-axis right there. And then point D. Point D is got another 6 and then another 8 from point C. So another 6 in the j direction and then up 8 in the k direction from there. So let's go ahead and count that out. 1, 2, 3. I kind of drew that axis a little bit funky, but 4, 5, 6. 1, 2, 3, 4, 6, 7, 8. So there is going to be point D. Alright, from there let's draw the forces. So the weight is pulling straight down from point C, so I'll go here, -500. And the other 3 forces are in tension, pointing away from that point. So I'm going to pull that right there. This one goes there, and this one points up toward that point. So let me label them. This would be CA, CB, and CD. Okay, that constitutes the free body diagram in 3 dimensions. The way to solve that is we need to find the forces in those 3 strings, the 3 unknowns. And we do that by finding the position vectors. So first of all, let's define the position vector of CA. CA, from C to A, we go -6 in the j direction and then +2 in the I direction. To find the unit vector, we take the length, which is the square root of the sum of the squares, and we divide the position vector by the length, and that gives us the unit vector. So 0.316 in the I direction, -0.949 in the j direction. Similarly for CB, I have -6 in the J direction, -2 in the I direction. Divide by the square root of the sum of the squares, we get that. And for CD, CD is +6 in the J, +8 in the K, same as over here. There's no change in the X direction, so I just get 6J, 8K divided by the square root of the sum of the squares, and I get that as the unit vector. From there, we have to find the force vectors. The force vectors, if you remember, are just the magnitude. In this case, they are unknown times the unit vectors. So I'm just going to rewrite these things. I'm just going to say that the force dA is going to be 0.316 times, I'm sorry, this is CA. FCA is going to be 0.316 times the magnitude of CA minus 0.949 times the magnitude of CA. Similarly with CB and CD, the weight is going to be only in the K direction, and that'll be -500 in the K. So now here are the 4 forces and their Cartesian vector descriptions. And now to solve, we just sum them up. So sum of the forces in the X direction have to be equal to 0. So write that equation. It's very important that you use this process. Sum of the forces in the X direction. So if I write it like this, then I can see that these are the forces in the X direction. These are the I components. So I just add those together. Now we can't solve for FCA or FCB, but we can just by observation and by arithmetic here, you can see that they are equal to each other. In the Z direction, those are the 2 components in the Z direction, and we can actually solve for FCD here. And then using these 2 identities, we can do some of the forces in the Y direction, which are these 3, and substitute into that equation using algebra, substitution method, and now we can solve for the final 2 unknowns. FCB is equal to FCA, and that's equal to 197.6. So here we've solved for all 3 of the unknown tensions using algebra, using the substitution method. This problem, 347, is slightly different, and when we try to solve these problems, it's important to understand the problems, understand what's going on. And often if you don't understand the picture, don't understand what's going on, you'll make mistakes in the solving of the problem. So let's look carefully at the picture, and you can see a little bit what's happening here. But there's a motor here that is winding up and making this string shorter. As it's making it shorter, it's rotating these legs about this axis. So these are called shear legs. They are in compression. Perhaps you can see that from the picture, but if you can't, then that's where some practice comes in. As they rotate going this way, the weight, whatever they're dragging out of the water here, is being pulled up and is also moving in that direction slightly. This up here is a knot, not a pulley. So again, what is the point of interest? What are the point we care about? This is going to be the point of interest. That's where we would sum the forces about as we're trying to solve this problem. And that's where we want to focus our free body diagram efforts. So let's look now at the origin that is given to us. So here we have X, Y, and Z, and here will be our origin. You can clearly see that point D goes backwards, but it is on the J axis. Point B is going forward and vertical, and then these 2 are on the X axis but have no change in either X or have no change in Y or Z. They're on the X axis. All right, let's go ahead and define the forces then. Forces are fairly straightforward. Well, no, first let's draw the free body diagram. That's what we need to do. So what I've done over here on the picture is found those points on my picture. So here's point B. Let's draw the weight. It's going straight down. 200 times 9.81. This would make that kilograms into newtons. We can see that D goes backwards from point B. It goes backwards 4 and then another 5.6. It also goes down in the K direction. So I'll just go ahead and draw that right there. That will be BD, and that'll be force BD. Now the two legs are in compression, and again, if you can't see that quite yet, a little practice will help us get there. So this one's pointing up in this direction, and that one is pointing up in that direction, and that will be from A and C. All right, now let's define those forces. Again, you can kind of go quickly once you get a little practice. FBD, we'll start with this one. It is FBD times the unit vector. The magnitude is unknown. It goes 0 in the I direction, negative 9.6 in the J direction, negative 4 in the K direction. And we'll define these as positive with a negative. Well, when we use the unit vector, the forces we'll find out if we have validated or we have the right sense, this right direction in these forces. So the unit vector would be 0I, make it divide by the square root of the sum of the squares, and there is our definition of our force. Similar FAB, FAC, and the weight. Once we define the forces, we sum the forces together. So let's do that. Now I can move the picture out of the way because we don't really need that anymore. Let's sum the forces in the X. I just look at the I components of the forces right here. So that would be negative 0.923 FBD. Negative. Oh, I beg your pardon. I am doing J's. Let me look at just the I's here. Here we go. Sometimes you have to be pretty careful here, but it'd be negative. Sorry, wrong pen. Negative 1/3 FAB and positive 1/3 FCB. Sum of the forces in the Y, and that would be negative 0.923 FBD and positive 2/3 FAB, and then positive 2/3 FCB. And then in the Z direction, I got negative 0.385 FBD plus 2/3 FAB plus 2/3 FCB minus 1962 equals 0. Alright, now once we have defined the forces, or the sums of the forces, now it's time to solve. What I want to do is show you a different way of solving. You could use the substitution method, which is perfectly legitimate, perfectly valid, and appropriate, but we're going to use RREF. And RREF, we talked about this a little bit in the 2D section, but it's a very powerful way when you recognize that you have simultaneous linear equations. And so what I've done here is just set it up the way I want you guys to set it up if you use this to solve this in your homework or on an exam. But what we do is we use the equations over here, and then we list the variables or the unknowns up on the top, and we put the coefficients of those variables in the matrix. So let's just look at the first one. Sum of the forces in the X is equal to 0. If I have AB and CB as my unknowns, I put the coefficients into that matrix, negative 1/3, positive 1/3. There's no constants, there are no constants in that equation, so over here the constant is going to be equal to 0. Similarly here with F, sum of the forces in the Y. Now look carefully at some of the forces in the z. I do have a constant here, but it is on the left side of the equation equal to 0 over here. When we set this up into RREF, what we want to do is set it up into this form. So what we'll do is we'll put the constants over on the right side, and if it happens to be a negative over here, when you move it to that side of the equation, it becomes a positive. Similarly, if it was positive on this side of the equation, once you move it to that side, when you put it into RREF on that side, it would be a negative. I'm not going to teach you how to use RREF here. It's just an appropriate time to just say this is a good method. So look at the tools that you have on Blackboard/course resources and figure that out if you'd like to use that. It's not required. It's just a very handy shortcut. Anyway, here you can solve for the 3 unknowns right like that. Well, what I want to point out here is that this is a really common error that students make. A common point of confusion is when a force is right along the axis. They have a hard time, you might have a hard time understanding what the unit vector is. And it's easiest, people understand always when it's going down. We know that the unit vector is always negative k. However, if it's going this way, this is a two-dimensional picture, that it's harder to understand for some reason that this is only in the I direction. So the force vector here is going to be F I. The force vector here would be whatever the weight is, negative k. So same thing over here in a 3D picture. Whatever the force in AB is just going to be FAB in the J direction. It doesn't matter how long that is. It could be 1 foot, or it could be 10 feet or meters or whatever. It doesn't matter. So don't get confused if you get a length here, because the unit vector is still going to be just positive J. Same thing with this one down here. Same kind of thing. This one will obviously have a negative k unit vector, but this one is only in the in the y direction. So this would be FJ, an unknown. Anyway, I hope that helps when we're doing these problems. And so let's look at one that is using that kind of understanding right here. And here is a point that is in equilibrium, that is basically already has the free body diagram drawn for us right here, so I don't have to redraw it here. But it's got 5 forces, and it's got 3 unknown forces that we want to solve for, F1, 2, and 3. So the way we do that is we define the forces. So let's go ahead and do that. And there is more than one way of writing these forces, so I'm going to do it just slightly different this time, but they all kind of work the same way. But I'm going to write the definitions of all 5 of those forces just kind of quickly. So F1, what does it look like? Again, we don't know the magnitude of F1, but we do know it's a vector. It's going to be the magnitude of F1 times the unit vector. The unit vector in this case is defined by the 3 angles alpha, beta, gamma. So I'm going to say that it's going to be cosine of 60 I plus cos 135 J plus cos 60 K. There's a perfectly good Cartesian description. Let's try F2. Magnitude is unknown, but it is only in the I direction, and you can see that it goes only in this direction, so all I have to do is just put 1 in the I direction, and that's all there is. And that's it. F3. Magnitude is unknown. In this case, it is only in the J direction, pointing backwards in the negative J, so I'm just going to put that as negative J, F4. Alright, what does F4 look like? F4, I guess I didn't really label here, but I'll call this one F4. And it looks like it is negative in the K direction, fairly easy to see. So it's going to be 200 as the magnitude, which is given, but only negative in the K. And then F5, I'll call this this force over here. That 800 is in the XY plane. So I'll say F5. Magnitude again is 800. And then what do we have? In the X direction, it looks like it has the 3/5 component going in the negative I direction, has a positive 4/5 component going in the positive J direction. So it'd be negative 3/5 I plus 4/5 J, and nothing again in the K. Now we have our 5 forces defined. All we have to do is now sum them all up, and I won't have to do that again for you, I don't think. I'll just show you the answers and you can see how you want to approach that. Some of the forces in the X is equal to 0, some of the forces in the Y, some of the forces in the Z. Using substitution method, fairly straightforward. What I've done is labeled these 3 equations. I started with equation 3, solve for F1, plug that into equation 2, and then equation 1. Using substitution method, we can also use the RREF method, and I put the coefficients of the 3 unknowns after I write the 3 equations. So it's real important when you solve this on your homework or an exam, to define the forces and then write the sum of the forces equal to 0 set of equations, and then how you solve them is going to be up to you. Again, you can use algebra or you can use this. Well, this last one we're not going to go through very carefully, but I would encourage you to to look at this solution and make sure that you agree with this approach. The reason I put this up here is it's using some of the things that we've talked about before that I thought were kind of interesting. First of all, the weight is being suspended here. FAD is along the x-axis, and this 3 feet is kind of a red herring. In other words, it doesn't apply to the problem. It doesn't really have anything to do with it. FAD is going to be FAD in the I direction as it's defined. The origin is here, and here you go backwards in the I direction for both of those. So those are kind of off in different quadrants than we have really looked at first or before. So again, what we're going to do to solve this is define those forces. So walk through each of those. Sum of the forces in the X, Y, and Z equals 0. Look at those carefully. You can use the substitution method, which I did there, or you can use the RREF method to solve for there. So please understand how to resolve those things, and I hope that this will be helpful for you.